Now let's use NanoVNA for something that can utilize both ports. So channel 0, the one that generates the frequency, and channel 1, the one that reads the signal back. So I have, say, this cable. I can measure the length, but I would like to measure velocity factor of that. So we're generating the signal and putting it into the channel 0 here. So let's say a signal that comes out of channel 0 looks something like this. So this will be our channel 0. So now the signal has to travel through this cable and come back into channel 1. So it will be the same signal that comes back, except it will be delayed by some value. Let's say this will be some t value. And this delay is solely determined by the length of this cable and electrical properties. So now let's say at channel 1 we get the same signal, the same frequency, but delayed. So what we can say it is the signal is shifted in phase, and we can plot it as well here. If this is the frequency and this is our phase, we can say for a given frequency we have some phase shift here. Now, if the frequency increases like this on channel 0, the delay will still be the same. So, however, what it appears that for a different frequency, the same delay will cause a different phase shift to the signal. So we can say that the shift can actually, the phase shift can actually increase. So we can say that it goes up and up and up and say until it reaches 360 degrees. And then it keeps on going to 370, or we can just say, you know what, we can just start counting from 0. So what our chart will look something like a sawtooth pattern. So it goes up and up and up, goes to 0, up and up and up and up, and then again to 0. Now from the perspective of channel 1, this phase shift, and because it is delayed, is actually inverse. So NanoVNA shows it as if it's going down, 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 and then we restart again at a higher value, then down, 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 and again at higher value. Now to calculate the electrical property or the length of the cable, we need to figure out the distance between these 2 points in, say, megahertz. So let me zoom in here. So let's, it's kind of hard to measure because there are way too many of these changes here in this purple line. What I want to do is I want to zoom in, where's my cursor? Here somewhere. So let's say we zoom in between 100 and let's say 200 megahertz. So we go to go back, we go to stimulus, and then start at 100 megahertz and stop at 200. Let's see what kind of picture we get. Okay, so we get this nice pattern here. So it goes down, up, down, 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 and then up. So we need to find the frequency at these peaks here, or these low points. So we go, so this is my cursor here. I'm going down, and then up, it jumps up, and the frequency that is shown here is 110 megahertz. So then, let's see if I can drag this cursor here. Okay, so now it's getting close. I'm coming here, and I'm almost there. So 171. Okay, so this is or 170. Yes, 171. 171 megahertz. Okay, so the difference is 61 megahertz. So every 61 megahertz, the phase shift will complete 360 degrees. So essentially it will be kind of reset. So to calculate how long the wire needs to be for electrical length to get to 61 megahertz, so the formula is very simple. So we take 300 and divide by 61. And it will be 300 divided by 61 equal 4.92 meters. I did measure the length of this cable that I have here, and it is 3.76 meters, the length of this cable. We need to also add this pigtail that I have here. It's about 10 centimeters as well. So we'll add 10 centimeters as well. So it will be 3.86 meters. So 3.86 meters is the total length of this cable that we have here. So to calculate the velocity factor, what we need to do is we need to take this actual length of the cable, 3.86, and we divide it by the measured electrical length, which is 4.92. So, and both of these are meters. And we get a ratio. So let's see, it's 3.86 divided by 4.92, and we get 78.4 and a half %. So this is what we measured with NanoVNA, the electrical length of this cable with this pigtail, with all these connectors happen to be. Now, I did write down the specs for the cable, and the specs for the cable say velocity factor is 78%. So which is very close. We got 78.4 out of 78% stated velocity factor. There is also a way to connect NanoVNA to a computer. So let's do that and see if we can repeat the same task of measuring the length of this cable only using software on the computer. So let's turn it on, connect USB, and start a program here. We rescan the ports, connect to NanoVNA. And once we get connected, we actually see the same chart that NanoVNA is seeing. Except it doesn't update automatically by itself, so we need to click this sweep data. So we can click it, and we get a new sweep results. So this time, instead of connecting it to both ports, we connect one end of the cable to one channel 0 port. Let's connect it here, and leave the other one open. So this way, what is happening, the signal travels through this wire, and since this one is not terminated, the signal will get reflected back to NanoVNA. And there is a way in the program here. We take a new sweep data. We can take a look at the time domain reflectometry, and what that means is essentially we will measure the length of the reflected signal. So let's click on that. And here we actually have a couple things. We can provide a velocity factor, and by knowing that, we will get the exact cable length. Or if we don't know, we can just leave it at 1, measure it ourselves, and come up with a velocity factor for this cable. So since we measured it at 78%, let's see if it exists. So it exists here. And the distance that NanoVNA is providing here of this measured cable is 3.84 meters. So the distance of the cable that we measured earlier, or by using just like a ruler was 3.86 meters. So the error that we're getting is on all this cable is only about 2 centimeters, and let's see how much it is. So it's actually about this much that we're getting error in terms of measuring the cable length. So I would say it's pretty precise by itself for given how small and how easy it is this NanoVNA thing is.